So let's get started again for the second to last lecture. Let's start with announcements. So we actually extended the deadline for exercise 3 by 1 day because we wanted to kind of let you take advantage of the final tutorial session, which is happening next week on the same day as today. So you can basically ask the last few questions to the tutor before making the submission. And there will be an exercise 2 recap today by Ankit after this lecture. If you haven't registered for the exam and if you still want to take the exam, then please register to make sure that we print out the exam for you. Was there anything? Oh yeah. So, and also I got some feedback from you for the last few lectures. I only have 2 more lectures to give, so it's probably irrelevant. But the feedback is always really mixed between you're too fast and you're too slow. So maybe that's also a good indication that I'm kind of in the middle. But also, I mean, yeah, I also felt like I wanted to give you kind of the feedback on the feedback, that I'm actually taking a look at the feedback. And if you don't feel like I'm not changing, even if you give feedback, I'm still kind of looking at it, but it's kind of mixed. So I'm not taking an action here. But also I feel like maybe what you're lacking is not really about the speed and the difficulty of the course, but maybe something else as well. So if you like to give more detailed feedback, like maybe that's also useful for my next lecture next year. So yeah, please, I'll be very happy, like glad if you share more more detailed feedback as well. And so next lecture will be the final lecture. There won't be any examinable material. That's how I try to design, right? Because you won't have much time until the first exam. So in the final lecture, I'm going to talk about the current projects at my university group, and also some of the potential master thesis topics, yeah, you might be interested in. And also, we are also collaborating with Matthias Bethke's lab. So we are also collecting ideas from their lab to do master's thesis on. So you might also be interested in kind of having a collaboration with the people there. Yeah, they basically don't have a lecture. Like Matthias is not giving lectures as far as I know. So they wish to kind of go through me basically to find good students. Yeah, and we also typically do Q&A session on the last lecture. So if you have any question that you want to get an answer for the whole class, right, you can always put it on Discord, or you can send an email. If there's anything else that you'd like to talk about or want me to talk about, right, in the last lecture, please send it to me as well. Okay, and then I'm going to jump into the lecture again. Right, so last lecture we looked into epistemic uncertainty. We looked into 2 major ways how you can measure this or estimate the uncertainty. One is Bayesian machine learning. You train a set of models, like infinite set of models potentially, and you basically look at the dispersion of the models, how much they disagree on a sample, and that kind of tells you the level of uncertainty for that sample. We can also measure distance because, like intuitively, epistemic uncertainty tells you whether your test sample is kind of far away from the training samples. And this far away is exactly what distance is trying to measure. So the idea is to measure this distance on the feature space. And by doing so, you don't have to kind of train a million different models, right, in Bayesian machine learning. And also, yeah, it's faster both during training and testing. Maybe you don't have to change anything during training either, right? So there are pros and cons for each of the approach here. And today I'm going to talk about aleatoric uncertainty and the factorization afterwards of epistemic and aleatoric uncertainties. So brief recap on what aleatoric uncertainty means. It's basically telling you, the model is telling you, I don't know, because I have seen some mixed signal during training. So for the same sample, sometimes I got a signal, yeah, this is class A, sometimes it's class B. And there are many different ways this can arise, right? So some people tend to focus more on one type of code, some people other types of codes. But I like to kind of just tell you that eventually all of these kind of different subcases are kind of different manifestation of the same cause, which is for the same sample or very similar samples, you're going to get different signals, supervision signals. And the model somehow has to take care of that. And then the model is then kind of modeling the aleatoric uncertainty. So for example, if you have a single class in an image, potentially, then, and that's kind of not confusing to humans, then we can say even the ground truth P of y given x is unimodal. And so it has low aleatoric uncertainty. Yeah, and if there are many possible answers from humans, right, then that's high uncertainty in terms of aleatoric uncertainty. It's not just happening in the low dimensional, low resolution images as in SciFar. Even on very crisp ImageNet images, you have these cases because you're supposed to just give single label per image. But eventually in ImageNet, you have a lot of cases where a lot of different classes are valid, equally valid for the same image. You may have corruptions in your image or some deleted features in your data. And then there is ambiguity afterwards. Conceptually, you can also draw a figure like this. So if you have two features available, then there's no ambiguity. But as soon as you remove one of the features, the samples get kind of mixed together. And for those regions where things are mixed together, you're going to get mixed supervision. And so there's higher aleatoric uncertainty. The same is true for generation problems, right? Whether that's image generation or text generation. Given the earlier part of the prompt, right, you may generate the next token sequence in different ways. Given the same caption, you may have different images that equally make sense, right? So this system will also be trained with a lot of different image and caption pairs where the caption is more or less quite similar, but the images are kind of very, very different. And then the model has to kind of cover all these possible diversity in the possible set of images. And that's also an instance of aleatoric uncertainty in more higher dimensional prediction task. So again, yeah, this is telling you that it's all about mixed supervision. And for addressing this, we need to kind of take care of two things, right? So one is architecture. You need to introduce an architecture for your deep neural network that is potentially making multiple predictions instead of like committing to a single prediction. And the second is a loss function, which is encouraging all these different hypotheses or different outputs from the model to kind of make sense, to basically follow the distribution of P of y given x. Okay. And here, again, the proper scoring rule pops out because it's then eventually also kind of fitting the distribution. Yeah, it's the problem of fitting distribution. And for fitting a distribution, proper scoring rule is just giving you an answer for that. So eventually, it's going to be architecture, which is accommodating different predictions from the model, and a loss function, which is just a proper scoring rule for the ground truth variations. Okay, so I'm going to talk about classification first, and then regression, and then maybe more structured regression or structured prediction, and that's it for aleatoric uncertainty. So I'm going to start with classification task, and here to give you kind of the mini conclusion of this section, I'm just going to tell you what we are doing is actually correct. And what we are doing is actually modeling aleatoric uncertainty sufficiently well. and we don't need to change anything. It's the same kind of conclusion that we made for predictive uncertainty, right? Where the task was a little bit different, which is kind of making a prediction whether I'm going to make a wrong prediction, right? But here the task is making a prediction or making a prediction distribution, which is kind of similar to or identical to the target P of y given x. It's a little different. So when it comes to classification, what a lot of people do is just take softmax on top of the logit values for the same dimension as the number of classes for your task. Yeah, and take softmax, which is going to give you a set of vector, like set of values, which sum to 1, and they're all between 0 and 1. And then you're going to put negative log likelihood on top of it. So you're just going to choose the dimension corresponding to the ground truth class and take the log of this softmax value and take the negative of that and minimize that value. Yeah, that's what you do when you train a classifier. And let's take a look at whether that's kind of satisfying these two criteria that I mentioned. So first of all, softmax output, right? It's going to give you a distribution over the classes, right? So in a sense, let's say even if the true P of y given x looks like this, this has some entropy basically, there's a possibility that the model can basically predict this. There's a way the model can kind of express this using appropriate logit values. So the model already has full capacity to express this. So that's what I mean by preparing an architecture which is conducive to producing multiple different outputs, yeah, which is already happening with the softmax architecture. Now, what about the loss function? Is it proper, right, for kind of encouraging the model to learn the true P of y given x? And that's the format we use, right? That's the negative log likelihood. We introduced proper scoring rule in lecture 9, but we only defined proper scoring rule for a binary random variable, like Bernoulli distribution. So on the one side, you have prediction, and on the other side, you have samples from the true distribution. So we had C of x, and we had L. L is only like binary samples from your true distribution. You're basically comparing these two through scoring rule, like log scoring rule. You can basically write the log scoring rule in this way, yeah. And that's actually identical to binary cross entropy. And we're going to extend the definition of proper scoring from binary random variables to discrete random variables. In terms of definition, there's a natural extension, which is, let's say there's a distribution Q, which is your predicted distribution, and let's say there's a true distribution P of y. So, you know, like when you have a discrete distribution, you can also write down, fully express the distribution through the mass function, right? And so P of y is essentially expressed as a set of weights, set of probabilities for each possible values. And Q is also expressed as a set of values for each possible value of y, okay? And then you're going to define the scoring rule as a function of Q and y, where Q is your vectorial expression of the estimated distribution, and y is the sample from the distribution. So y will be kind of the index of the random variable, basically. And we say it's proper when the expected score, expectation of S, given where the randomness is coming from the samples y, this is maximized if and only if Q is truly recovering the true distribution P. Okay, so it's the same definition as before. So, you know, we wrote Q in the previous slide, but that's basically expressed as a set of softmax outputs in terms of a neural network. So let's say that's f of x, right? That's the output of the neural network f, which is eventually a softmax output. And you have some true categorical distribution, P of y given x. And you only get samples from there, which means you only use the ground truth labels for each sample, okay? And using that, you can basically compute the log scoring rule, which is given by the summation over k, where yk is a one-hot vector. So if k is equal to, so yk is basically a one-hot vector, right? Indicating where the true value is. So if y is actually 1, right, then you're going to have one value 1 at index 1 and 0 everywhere else, okay? And then log of f of x, right, which is the softmax output of the network. So that's my scoring rule, and it's called log probability scoring rule. And we have a result saying this is proper scoring for the recovery of the true P of y given x. And that's actually left as an exercise for you to try out, but this is quite important. This involves kind of doing, checking the first order conditions for optimization and making sure that you also apply the boundary condition of that the sum of f should be equal to 1. So you may use the Lagrangian formulation for the optimization and optimality check. Yeah. Yes.
Is it right that there's no minus sign?
So it's always confusing, but for scoring rule, you always care about the maximization. So you look at the log likelihood, but in deep learning optimization, you like to do minimization instead. So you put minus in front. Yeah. As long as you stick to one of these, it's all fine. Yeah. At the code level, there's no difference. So far so good. Yeah. Just a simple extension. But the reason I'm talking about this and spending time on this is because a lot of people are still very confused or surprised that cross entropy laws that we normally use are encouraging this kind of higher entropy solutions. So a common misconception that a lot of people, even those who have been spending a lot of time with deep learning, they have some misconception that this cross entropy is actually encouraging very low entropy solution. It tends to give you very high confidence solutions. It tends to be overconfident, basically. But that is not the case. That is not the case. It's a proper scoring again, so the model is fully encouraged by the loss function to be exactly following the true distribution. So to convince you that this is the case, I'm going to give you some toy example here, where the true distribution is kind of given from this plot, right? So these are actual samples from the true distribution, where the class 0 and 1 are coming from Gaussians, different Gaussians with different centers. And the true y given x is given by the Bayes theorem. It's not even Bayes theorem, it's just the definition of the conditional probability, and that's going to be f of, this is Bayes theorem actually. P of x given y over P of x given, well, it's basically P of x at the bottom, but we kind of split this into two different cases, where y is equal to 0 or y equals to 1. And like we're going to have the same probability, same prior probability for each of the class. So let's say P of y equals to 0 is 0.5. The same is true for y equals to 1. So they all kind of disappear from the equation. And you're going to have just a comparison of the likelihoods between likelihood of x given whether the point is from class 1 or class 0. you're just gonna check the ratio of these two likelihoods. And yeah, this is the final formulation. And we can fully compute this. And so for each kind of grid point, I computed this and kind of drew this true P of y given x, given this generative procedure for the points. So the question is whether, if you train the model with the cross entropy loss, are we actually going to recover this exact function for every input point? Okay. So what I did was I trained the model with this cross entropy loss, and well, of course, you're going to see a lot of mixed supervision along this. X1 plus X2 is equal to 0, because there are a lot of overlap here. And you know, like, this is the learned function, and this is actually identical to the ground truth function of P of y given x, almost, right? So if you take the difference, you're going to see a little bit of mismatch when you move away from the training set, when you have higher epistemic uncertainty. But as long as you have sufficient number of training samples around, your estimation of the true aleatoric uncertainty is quite precise using the usual cross entropy loss. And this also concurs with my personal experience with training with neural network. Usually when you have a lot of mixed supervision during training of a deep neural network, you're actually going to find that the neural network really understands this and will represent the P of y given x quite precisely. Okay, so that was it for the classification case. Let's move on to the regression case. Now the setting is the usual kind of regression setting, right? So now P of y given x is not an index. You know, y is not an index. It's a continuous variable. And so the P of y given x will be kind of continuous. Okay. The true distribution, we can say, yeah, that's the usual kind of definite kind of assumption in regression, right? So P of y given x is Gaussian. So it's going to follow some mean curve, mu of x, right? So for every x, you'll have different points. Mu is typically kind of smooth, right? But there's going to be some noise in the generation process, right? But here, in usual regression problem, you assume the same kind of noise for every different x. So noise is basically independent of the input. Yeah. It's called homoscedastic regression. But for the purpose of aleatoric uncertainty, you want to have different kind of aleatoric uncertainty depending on the position of your x, right? I mean, that's what classification is all about, right? Depending on where you are, yeah, you have different degree of aleatoric uncertainty, right? If you have the same kind of aleatoric uncertainty throughout the space, then there's no reason why you want to measure it. So you want to introduce different levels of noise in your true y given x at different x, and that's what heteroscedastic regression means. And the way you write this down is by putting sigma of x for your noise variable. The goal is to learn the functions mu of x and sigma of x. Okay, so typically in regression, you just learn the mu of x, but now you have to learn two functions, mu of x and sigma of x. So yeah, this is visualization of what heteroscedastic regression looks like. So if you have the homoscedastic regression, you're going to have the same width of the band throughout different values of x. But now you have different degrees of noise at different location of x. And you have to model both of these variables, both of these curves. Yeah, this is another visualization. So we can have two different sources of again, uncertainty. So in this region, you're going to have a lot of training points, so you'll have lower epistemic uncertainty. But now the band, right, of the possible values of y is quite dispersed, so you're going to have higher aleatoric uncertainty. If you don't have any data point, then you're going to have higher epistemic uncertainty. So, I mean, when it comes to heteroscedastic regression, there are a lot of different use cases. So, I find it super interesting to kind of look at this dense prediction task where you're given an image, for example, and you have to predict for every single pixel what is the value that I care about. In this case, the depth of the scene, right? And you know the depth of the scene, like inferring the depth, is a rather ill-defined task, and you have to rely a lot on the priors and and for the same kind of scene, right? Let's say you have a whiteboard, right? And whiteboard is probably not going to tell you much about how far away the whiteboard is from you. So during training, you're going to see a lot of whiteboards at different depths, right? But eventually, you're going to see the same kind of signal for all these cases. And so, in other words, you're going to have different. You're going to have the same kind of pixels for the whiteboard, but in each case, you're going to have different supervision signal given by the depth, the true depth of the whiteboard. And that's one example of heteroscedastic regression or data points with high aleatoric uncertainty. So when you can do this, then you can basically not solve it, but you can model, at least model the level of uncertainty. So for training this, again, we need to extend our definition of proper scoring from discrete to even continuous distribution. And the way you represent a continuous distribution in many cases is by writing down the PDF density function. So let's say our Q of y is the density function for the predicted density function, and P of y is the true density function. Okay, then we can define a scoring rule like S of Q and y, and we say it's proper when, again, the expected value of this under the true distribution y is maximized if and only if Q is equal to P. And one example of proper scoring is, again, log probability scoring rule. So for every density, for the density function, you're taking a pointwise log value at each point in your density, and that's it, right? When a new sample y comes in, you're just going to measure the density value at that y point, then take the log of that, and that's your proper scoring. And again, this is an exercise to show that this scoring is proper. In other words, the integral over log of Q of y, where the weighting is given by the true distribution P of y, this is maximized if and only if Q is equal to P. Actually, this is one of the most famous kind of inequality that appears a lot in probability theory. It's also closely linked to Jensen's inequality. So you can basically derive this from Jensen's inequality as well. So we leave this as an exercise. If you have any question about this, you can also ask Lennart as well, because I think this is part of exercise. Or ask me as well, yeah, doesn't matter. Now, so we are going to use this log probability scoring rule to train a model to predict the true mu of x and sigma of x, okay? Maybe that's a little vague, or maybe it becomes less vague after the full formulation of everything here. So, you know, we started out with the assumption that the true distribution is Gaussian with the center at mu of x and the variance given by this standard deviation given by sigma of x. So our aim is to train a model which has basically two heads, right? So one head is responsible for mu of x, and the other head is responsible for sigma of x. Do you know what I mean by head of a network? You can think of like two networks with an output. So depending on the dimensionality of the output space, let's say it's one-dimensional, right? Then one neural network is kind of producing a single scalar at the end of the computation, given the same image. And there's another model which is giving you another scalar value for sigma of x. You have a choice here. You can make these two networks kind of weights independent from each other, or you can share maybe some of the early layers of each of the network in the same network and just do bifurcation or separation of the heads in two different set of parameters, two different layers in parallel. And then they are kind of producing mu of x and sigma of x respectively. So that's what I mean by having a two-head architecture for the neural network. So that's the architectural kind of preparation that we need for training this. Now for the parameters of the, for this predicted distribution, the predicted PDF, okay, the predicted PDF will be given by the Gaussian PDF, where you plug in the predicted mu of x and the predicted sigma of x. And then assuming that these are the true parameters of this Gaussian, you measure the PDF at point y. And that's going to give you the likelihood of x and y. Is that clear? Or that's usual likelihood computation for linear regression. The only difference from the usual homoscedastic linear regression is that now sigma of x is a function of x as well. Normally, it's just treated as a constant. Of course, you have to take log likelihood, right? Or negative log likelihood. So you put minus log in front and try to do minimization of this. And like this is in a nice form where you have log and x inside and a lot of multiplication, divisions inside. So you can basically do reordering everything, kind of simplification, and you end up with this formulation down here, which is given by 1/2 sigma times mu minus y squared plus 1/2 log of sigma squared of x plus some constant, which we don't care about because we are solving a minimization problem. So maybe we can take a look at what this really means. So, when sigma is treated as a constant, regardless of the value of x, then we can simply get rid of this term. Yeah, and we can also probably get rid of this term as well because it's a minimization problem again, right? And a scalar product that's kind of put in front of a single term in optimization, they can just got rid of. But now it's not, right? So you need to keep both of the terms here. So if you look at the first term first, right? It's actually an L2 loss for obtaining or optimizing the mu of x, and that's exactly what you do in normal linear regression problem, right? So that's the same, but now it comes with some weighting term given by 1/2 sigma squared. So what does this tell us, right? So let's say the model assigns a higher value for sigma of x, yeah, and then the penalty for not estimating y correctly, which is given by this L2 loss, will be less penalized, right? So the model has a choice to kind of put higher value of sigma for a certain data point, and then the model will be kind of excused for making a wrong prediction for y, for mu of x. That sounds good, but then if you just have this term, then the model may just choose to set very high value of sigma for every data point, and then just give up on making any prediction. And then comes the second term here, which is kind of giving you a penalty for setting sigma of x too high in any case, right? So in a sense, this second term is kind of giving you a budget on how much uncertainty in general you can assign to any point. And then the role of this model is to basically make a smart choice on which samples I need to kind of pick higher value of sigma, on which samples should I pick lower values sigma. And the fact that this is proper scoring kind of ensures that after all these kind of complex choices that the model makes, it is encouraged to recover the true distribution, true mu of x and the true sigma of x. So again, we have some sanity check if that's the case in toy case. So I basically built this data set by asking ChatGPT, I have this lecture and can you generate a data set for this? And yeah, it's producing a very good data set for that. So we have different band, the width of the band at different x point, right? And so this is the true mu of x and sigma of x, and these are the samples from this true distribution. You're going to train with this. And that's the actual prediction that, that this loss function gives, right? So I can see, at least from my eyes, that it's not just the mu, but also the sigma that's predicted pretty accurately. Yeah. So that was it for the regression, like simple linear regression case. And now let's take a look at some harder case given by complex outputs. So let's say you're interested in future prediction task. There are different degrees of futureness, right? So in one case, you might be interested in like predicting the future in a few milliseconds, right? If you care about making money within milliseconds, or at the scale of kind of making prediction for pedestrians, because maybe you want to avoid them or pick a route which is safest. Maybe that's a matter of a few seconds. But like as this time window grows, the future distribution becomes very, very complex, right? So maybe it doesn't make sense to just model the future with a single Gaussian. And maybe you have to introduce something more general. And this something more general is usually expressed in probability by mixture of Gaussians. So in this case, you can have, for example, 3 mixture of Gaussians. And that encodes something much, much more complex than just a single Gaussian. The same is true for more complex generation tasks like image painting. Given the context pixels around this blank, what should be the right value for this gray region, right? That's in painting. And there are thousands of dimensions, and there won't be a single solution, single distribution that makes sense expressed by a single Gaussian. So in this case, again, it probably makes more sense to consider multimodal kind of distribution. So here, again, the common challenge is that the aleatoric uncertainty is present. Yeah? There may be multiple possible outcomes given the input. And a single Gaussian probably doesn't make sense. So what we can do is to kind of assume that the distribution is mixture of Gaussian. So Q of y given x, your prediction, is given by the average, the sum over multiple PDFs given by a single Gaussian with different means. So each Qm will be a single Gaussian given by Fm of x, which is the mean for distribution m, okay? But you're gonna have multiple of these, right? And to make things simpler, we can just make sigma a fixed value now. Yeah. So the only variation is only coming from the positioning of different factors, different Gaussians in the mixture. Okay. So we are kind of giving up on the modeling complexity for sigma, but there are a lot of theory around this kind of mixture of Gaussian, saying that this is general enough that any kind of basically integrable function, right, Lebesgue integral function, can be approximated by a mixture of Gaussian as you increase the number of components and as you decrease the variance for each component. There is always a possibility to approximate more and more complex functions, as complex as general integrable functions, which contains like all differentiable function, all continuous function, maybe piecewise smooth functions, and so on. So it's very powerful, and so I'm quite happy with just using mixture of Gaussian instead of something more complex. So that's what I mean by universal approximator. Yeah. So maybe after this slide we can take a break. So another way to interpret this is through mixture of expert. So we can think of each mu here. So you can think of this as mu or f, right? So these are basically different means from different components here. They can be taken care of different, like they're expert in their own area, okay? Because what you typically see is, so maybe I can give you some example here, right? So maybe one of the heads, one of the expert is very good at generating a person in the scene. Maybe one of them is very good at generating like natural scene. The other one generating cars on the street, right? So that's what you typically observe when you have multiple experts. They're kind of specializing on their own expertise afterwards. I think because that's more kind of efficient way to use parameters. And so yeah, this is how you model your deep neural network to kind of accommodate different possibilities. So you maybe have a shared trunk to save the number of parameters, and then afterwards you have different branches leading to different heads, and these heads are kind of specializing in different part of the problem. And you're eventually training all of these through some proper scoring, right, again, which is then kind of incentivizing each of the experts to kind of do well on their own task. In the next part, I'm going to explain intuitively how proper scoring is encouraging each of the experts to specialize on their own task. Okay, so welcome back. I'm going to talk about proper scoring for mixture of Gaussians. Again, this is a continuous distribution. So the scoring rule itself is the same. Log of the PDF value at the observation, right? Which is given by, minus log of Q of y given x. And again, Q of y given x is expressed as a sum over Gaussians. Okay, so you're gonna put a minus log. Yeah, it's a loss function, so I'm gonna put minus to minimize it. Minus log of the average of the density functions for each of the Gaussian that you're modeling. So that's the loss of interest. And for understanding what this loss function is actually doing, I'm going to take a look at the kind of dissect this loss function in terms of the loss function for individual Gaussian. we understand what individual Gaussians are doing, right? These are all, yeah, proper scoring. You know, like when you put minus log in front of this PDF, then that's exactly proper scoring for that particular mode, the Gaussian. What happens, you put it on the average of these, okay? So I'm going to show you some intuition around this, first with some mathematical derivations, and then connect this to other types of loss functions that appear in different literature in machine learning. So this is the mathematical formulation that I wanted to introduce today, and I love this formulation actually because it tells me so much about what, how the putting a negative log likelihood in front of some mixture is kind of distributing the supervision signal to different heads, different experts. So eventually, I'm going to take a look at I'm going to express the derivative, the gradient of the loss value against some parameter L, some arbitrary parameter in the network. I'm going to express that in terms of in terms of the individual gradient for the individual loss, expert-wise loss value. You're going to have a single weight value per expert eventually. So I'm going to take a look at what this weight means. Maybe it becomes more clear when I go through this one by one. So let's say we're starting with some the gradient of L on some parameter L, and then we just plug in the log likelihood inside, and we can do chain rule on the log, right? So on the denominator, you're going to have the same value as what's inside the log. Then you have the derivative of what's inside the log on the denominator. Usual. And by linearity, you can swap this gradient with the summation. And you can basically get rid of 1 over m above and below. And you can plug in the definition of qm of y given x for both numerator and denominator. Yeah, that's it. And then you have now chain rule on exp, right? So you have the function itself replicated first, and then you have the derivative of the inside of the exp. Okay. So the minuses kind of go away, and this 1 over 2 sigma square is constant, so it goes out, and you have derivative of this L2 loss. Now we're going to define this exp of this term inside divided by the sum of our exp of the term inside with different values m. We define this as WL, okay? Yeah, WL. And you know, like maybe you noticed that this is in the format of softmax, actually, right? So in other words, it's the softmax over the vector, which is given by this minus 1 over 2 sigma squared times the L2 loss. And then you have the rest of the terms on which you can introduce basically minus log and exp together. Minus log exp and minus, okay? So together they all kind of disappear actually. So it's an identity mapping if you do all these 4 sequence of operations together. So you just plug them in between the derivative here and the term here. And then you realize that this log of exp of this is actually, or exp of this is actually QL of y given x. Okay, so you plug in QL of y given x, and that's precisely the derivative of the loss value for this expert L. Okay. So we reduce the gradient for the whole mixture of experts into a single expert. So it's all identical, right? The gradient is all identical except that there's a factor WL in front. And again, this is a softmax over, and you know, like what's inside this is also kind of a loss value, right? Minus loss of index L. So you can write down the value here as the softmax over the loss values for each of the experts. Okay. So what does that mean, right? Yeah, yet another way to write this equation down is to say, actually, you know what? You can write down your loss value for the whole network as a sum over individual loss for each expert. You can basically train each of the experts individually, except that you just want to put WL and you don't want to pass the gradient through this WL, right? And WL is again the softmax values. So what does this do, right? So the way I like you to think of this is you're going to have multiple experts. You're going to have multiple losses for all the experts. Maybe some of the heads will have higher loss. Some of them will have lower loss for this particular sample X and Y pair. So let's say this is the now WM, right? So WM is actually softmax of minus L. So the highest one here corresponds to the case where the loss is the smallest. So basically, this is the expert which is the most correct. So x-axis here is the expert index. So this is the most correct one, and this is kind of telling us that the weight for this expert will be the highest. So if one of the expert is the most correct, then this most correct expert will be given the greater weight. And you know, this is a loss-based training, so if you get more weight, then there will be more penalty actually. So it's kind of funny that if you're more correct on this sample, you're actually going to get more penalty. You're kind of pushed to be even more correct on this sample. And vice versa. For the other experts who are wrong in the first place, they won't get much signal. They won't be pushed to kind of be right on this sample. So you see what this is doing, right? Maybe for the first few iterations, maybe because of some randomness, maybe some of the models, some of the experts will be better at certain types of samples, maybe the others more at the other types of samples. But these kind of initial perturbations, distributions, get amplified in the course of training. And they become even better and better at solving certain types of tasks. So this is how you encourage kind of expert system of experts, which is quite exciting, at least to me. And I wish to also discuss the role of sigma in this process. So you know what temperature in softmax is? You all know it. So it's basically a term that's multiplied in front of the logit values. So let's say you you have some logit vector and you can multiply each of these by some temperature T, usually 1 over T. So let's say it's 1 over T, and let's say T is huge. Okay, so temperature is huge, and then the factor will be close to 0, and your logit vector will be all kind of 0. If you take the softmax of this, then it's going to be a uniform distribution. So when the temperature is higher, your softmax value will be close to uniform. When the temperature is lower, let's say minus or close to 0, it can be minus actually. And then the factor in front of the logit will be close to infinity. And that's actually going to even push for the dominance of the max element in the logit, in the softmax. Because you're putting exponentiation on top of the logits, the argmax value, the max value gets even more pronounced. Even if maybe the difference between the max value and the second max value is small, but as long as there's a difference, this small gap will be exaggerated when you put a huge constant in front. And so eventually when the temperature goes down, you're getting closer to a one-hot vector after doing softmax. So sigma is essentially doing the temperature parameter because it's in the form of 1 over sigma squared, right? So when it goes to infinity, you're putting almost equal weights on all the experts. When it goes to 0, then you're only penalizing the most correct one, and you don't care at all about the other samples. Other experts in the system. And this sigma is kind of controlling how much diversity you're going to induce in this system of experts. So for example, if you're training all the experts equally, then they will be more or less equal on every sample. If you're just penalizing the most correct one, then it probably doesn't care about whether each of the expert is doing the job correctly or not. Maybe all you care about is whether all the experts are different. So there's a trade-off between being correct, making sure that every expert is kind of correctly solving the problem, and the diversity of the expert. If you make the diversity too great, then even for a very certain sample, you need to still diversify all the experts, and since there's only one correct answer, in many cases, you basically have to be wrong in order to be kind of diverse. So this is the trade-off that sigma is controlling. And the special case when you're only training the most correct answer from a system of experts is called k-diverse loss. It has a name, actually. It comes out from many other contexts in machine learning. It's also called min loss because you're taking a look at the loss of multiple different proposals from a network or from a set of networks, and you're only training the one with the lowest loss. And that's called min loss. Yeah. And as I said, this comes out in many contexts. So in diverse net, for example, it comes up as a C variable here. So you're only penalizing the expert C with the lowest loss value here. Yeah, this is called mixture density network. And again, here, you're only taking so this is one-hot vector for the argmin of the loss value here. And you're only training for that index here, I, the index I, which is argmin. They call it winner takes all loss, which also kind of makes sense. So in summarization, aleatoric uncertainty is very simple if you put a proper scoring rule, regardless of the format of the distribution, then it's probably going to solve the problem for you. Maybe you have to do a little bit of engineering in terms of how to put the heads on the network and how to make sure that different proposals are generated from a network or from a set of networks. But eventually, it's just about putting a proper scoring rule. Now, let's talk about the final topic of the course, actually, for the exam part. Factorizing uncertainties. So far we talked about largely 3 types of uncertainties. So one is predictive uncertainty, epistemic uncertainty, and aleatoric uncertainty. So, what we did for each of the uncertainty was kind of well motivated, I would say, in each case, right? But let's take a look at them in more totality. So for example, for predictive uncertainty, we looked at max probability or entropy of the prediction vector, right? And then for epistemic uncertainty, we looked into Bayesian model averaging, maybe taking max prop or entropy after doing Bayesian model averaging, okay, and take that as the epistemic uncertainty. Or we also looked into measuring distances in the feature space. Now for aleatoric uncertainty, we talked about making a parametric module which is supposed to also give you the variance, right? So it could be in the form of sigma of x, part of the network, or it could be in the form of different mu of x for different components in the mixture of Gaussian. And then putting a proper scoring rule. So the natural question here is this max prop of prediction vector only valid for predictive uncertainty and not for epistemic uncertainty or aleatoric uncertainty? Or when you take the max prop of Bayesian model averaging, is it supposed to be just measuring epistemic uncertainty, or is it potentially also measuring aleatoric uncertainty, right? So, I mean, these are supposed to be different sources of uncertainties, and ideally, they should all encode different variations here. The question is whether that is the case. So maybe we can take a look at this at a more conceptual level, how these are supposed to be related to each other. And in practice, kind of taking a look at them separately makes a lot of sense because they have different use cases. For predictive uncertainty, we need them because we need to kind of abstain from making prediction, for example. When I'm going to be wrong, when I know that I'm going to be wrong, then I should probably stop there and ask for help from a human. Epistemic uncertainty is useful when you try to do active learning or exploration. You basically know that I haven't experienced this before, so I need to be a bit more cautious here, or I need to actually get more data from here in order to be better at this kind of samples, right? And that's also related to hallucination problems in large language models. People like to connect epistemic uncertainty with the hallucination problem, which means the model likes to generate a fact which is not true. And the usual reason why they would do that is because they are kind of generating something that's outside of their training domain. Although I'm not entirely sure if that's the story is that simple, but I think it's true that there's a close relationship between knowing what I don't know and the hallucination problem. And then aleatoric uncertainty is useful for generative prediction. You don't just generate a single answer. You may be interested in generating multiple plausible answers for the same question. So these are all different applications, and for practical reasons, you might want to get different scalars for these three different values. So it'd be quite funny if C of x is actually encoding PU of x and EU of x and AU of x simultaneously. So these are all standing for predictive, epistemic, and aleatoric. So the question is, does it actually encode only one of these, or does it encode many of these at the same time, and so on? Or the other question is, can we somehow design C of x to be kind of specialized in each of these separately? So we have C1 of x and C2 of x and C3 of x for each of these, for example. So one of the mainstream approach in this domain is to try to establish that predictive uncertainty is actually the sum of epistemic and aleatoric uncertainties. Why is that? Because conceptually, that kind of makes sense. Predictive uncertainty is asking the question, how likely am I going to be wrong on this sample? Okay, and with a bit of kind of pushing the boundary, you can describe epistemic uncertainty as the question of how likely am I going to be wrong because I haven't experienced this before. Although this may be disputable because maybe epistemic uncertainty could be defined as how much new this is without caring so much about whether I'm going to be wrong because of that. Yeah. but I can also see their point when people try to argue that um, the cause, the epistemic and aleatoric parts are kind of dissecting the possible causes of being wrong for this sample. And aleatoric uncertainty is basically how likely am I going to be wrong, because I have, even if I have infinite experience, right? So now EU and AU are kind of complementary to each other, and they sum to a whole, right? So they're basically complementary of each other. So in that case, it kind of makes sense to say PU of X is actually the sum of EU of X and AU of X. So along this line, I'm gonna introduce two approaches which are kind of trying to establish this, and maybe a third approach which is kind of independent of all this, but still try to predict EU of X and AU of X separately. So the first approach, information theoretical decomposition of predictive uncertainty. So they start with some Bayesian machine learning, right? So they're going to have some posterior Q of theta, okay? And let's say we're talking about classification problems. So we can write down the full predictive probability by the samples of models theta m from Q of m for each class K. So it's kind of a matrix of probabilities where one axis is different samples from the posterior, and the other axis is the set of classes. We can define, I think it kind of makes sense to kind of define PU of X as the entropy of the BMA. Although in the epistemic uncertainty part in the lecture, we define that as the epistemic uncertainty, right? But some people like to say, yeah, this is actually predictive uncertainty. Yeah. So I'm not trying to commit to any of the definition here, like any of the match between computational object here, and there's human-defined kind of uncertainty. Sometimes it makes sense to just say, this object here is actually epistemic uncertainty. Sometimes it's also correct to say it's predictive uncertainty, because the definitions are not so firm. So yeah, in other words, you won't be penalized to kind of call this in any way in your exam, for example. Yeah, and also in your research community, they won't complain that you're defining this in any way, right? It's a very young field in that sense, right? So it's very exciting as well. It's good and bad. And AU of X, the aleatoric uncertainty, for example, you can think of that as the average entropy over the posterior. So for each posterior sample, you're gonna take a look at the entropy of the predictive distribution, and you're gonna do average of all these entropies over different samples of posteriors. So in other words, P of X is given by entropy of average of PMK, and AU of X is kind of the other way around. You do entropy first, and then do average. So far, it kind of makes sense to me as well. So what does that mean, right? So I'm going to convince you why that makes sense. So you have a matrix like this. So the X is kind of the model, the different posteriors. And for each posterior, you're going to have the prediction. For class 0 and 1, you're going to have 30% and 70%, and so on for these classes. And then if you take the Bayesian model average, you're going to have 0.525 and 475. On the right side, you have a different set of models, different posterior basically, with different kind of predictions. But eventually, when you take the Bayesian model average, the prediction vector will be identical. So in that sense, your predictive uncertainty will be identical to each other for these two sets of models, or for these two posteriors. The entropy is basically 0.3. But now, which all makes sense, but now I'm going to claim that um, the first case has higher, sorry, um, no, lower epistemic, sorry, higher epistemic uncertainty and lower aleatoric uncertainty. And on the right side, you have higher aleatoric uncertainty and lower epistemic uncertainty. So let's take a look at the right side first. So all these models are kind of agreeing that on this particular sample, class 1 and 0 are almost equally likely with close to 50% each. Okay, so your entropy values will be generally high in all these cases, all these post areas. And that kind of means to me that these sets of models have seen during training basically this sample. And this sample is somehow some high aleatoric sample. P of y given x is actually equally distributed between 0 and 1. And since you have seen a lot of these signals, all these models are kind of trained to be like, trained to kind of distribute this, the prediction to 0 and 1. On the other hand, on the first set of models, basically these models seem to have a lack of training. So the models basically do not agree so much among each other how they need to take care of this sample. So sometimes they are, yeah, I'm confidently class 0. Sometimes say I'm confidently class 1. And to me, that's a signal that there has been not so much training for this sample. And so I'm going to say, yeah, the left case is basically higher epistemic uncertainty case, and the right is higher aleatoric uncertainty case. And you know, we set out with the premise that Pu of x is equal to the sum of Eu of x and Au of x. The fact that the the aleatoric uncertainty is, sorry, epistemic uncertainty is higher here means that aleatoric uncertainty is lower here, and vice versa. So in more kind of formalized equations, you can write down Pu of x as the entropy over the Bayesian model average, which is given by P of y given x without the posterior theta. And Au of x is first doing the entropy of each posterior for the y-axis, the class axis, and then taking the average over over different posteriors. Okay, so that's more continuous way to write this down than this discrete classification case. Okay, I'm doing this because I want to write down epistemic uncertainty as the difference between these two, between Pu of x and Au of x. Okay, and it turns out that this is actually equal to the mutual information between y and sigma. Yeah, I'm writing this down because it's a neat way to kind of consider the difference here. And it also kind of makes sense because epistemic uncertainty is telling you how much you have experienced this sample. And this mutual information is basically telling you how much overlap in the information between your posterior and your the true distribution of the class has for this particular x. So yeah, so you see the logic here that we start off with the plausible definition of Pu of x and Au of x, and then define Eu of x as the difference between the two. And then incidentally, Eu of x turns out to be this mutual information, and the mutual information kind of explanation also seems to make sense. Does it make sense? No? Yes? Or yeah, we can move on and maybe come back to this if you have any question. There's risk-based decomposition as well, which I don't like so much, to be honest. But you'll see why I don't like this. So they do the same thing here. So they define PU of x and AU of x from some plausible definitions, and then define EU of x as the difference between the two. So first, PU of x is defined as the risk for my model f at input x. And risk, you're probably not so familiar with risk, and risk is basically the expected loss. And you can write down the loss as at a particular data point x as the loss value basically for the observation x and y here, and then you take the expectation over over distribution of y given x. And you know, this is not a value which can be computed actually, because you don't have access to the true py given x. Here x is fixed, right? So maybe you can do some kind of search in your training set with the same x but with different y, right? And then do the average of the loss there as the predictive uncertainty here. But you know, like, it's rarely possible that you can find the same duplicate instance in the training set for x and then find a lot of different samples of y. So it's essentially impossible to compute in general. Some work here, DUP, they advise you to train a separate module for predicting this risk, yeah, given x. And I don't really like this approach because you have to train a new model for this. But just to give you an idea of how people have approached this, I'm just introducing this this one as well. And then the aleatoric uncertainty is defined as the expected loss when you have actually trained the best model for this particular sample. So basically, the loss minimizing f of x, so not just for this particular y given x sample, but let's say you have a population of y for this given x. What is the function that's minimizing the average loss for this sample? I'm going to set that as f of x, okay? And then I'm going to compute the loss value for this prediction on this x. And that's your Bayes optimal prediction, Bayes risk. And now this is independent of the particular function that you have learned here. You're just going to take the optimal function, not necessarily the function that you have learned, and that's going to give you the aleatoric uncertainty of this sample. It makes sense because you know, aleatoric uncertainty is independent of the function that you're learning, right? It's inherent to the data and not the model that you're learning. And so as long as you can compute this, then yeah, that's good. I mean, I agree with this definition. But again, the problem is you don't have multiple samples of y given the same x, right? So again, what this DUP paper advises is to train a separate network for estimating this for every x. And again, epistemic uncertainty is just the difference between r of f and x and r of x. So, and this is always greater than 0 by the optimality of f, okay? So the risk will always be higher than the optimal risk. So, which is a nice property for epistemic uncertainty. You want this to be positive always, right? So that was the risk-based decomposition. Now we have not necessarily a decomposition, but like independent estimation of aleatoric and epistemic uncertainty separately within a nice computational graph, like a single computational graph. So let's revisit the log likelihood objective for heteroscedastic, it's always hard, heteroscedastic regression. You have negative log likelihood given by the two terms, right? You remember. And you know, the computational graph looks like this. So given X, you're going to have a deep neural network predicting mu, and another deep neural network predicting sigma. Maybe these two deep neural networks share the same trunk, like the first part, maybe just the different heads. But anyways, you have deep neural network on both sides. And then you're going to put log likelihood on top of the predicted mu and sigma through this this computation, this loss value here defined. Of course, you also plug in the observed y as part of the likelihood. And then by the properness of the log likelihood, it's going to give you the true Aleatoric uncertainty, sigma square root of x. Now the question is, okay, now with this you can compute Aleatoric uncertainty. Can you also compute epistemic uncertainty with a similar kind of computational graph? Is there a proper scoring rule that involves not just the aleatoric factor like sigma here, but also some other factor that's kind of encoding epistemic uncertainty? And the expected advantage of this is that typically for epistemic uncertainty, we needed to use some kind of Bayesian model, and we had to do a lot of Monte Carlo sampling at test time. So that means you have to do inference several times and take the average or variance or whatever to kind of estimate the epistemic uncertainty. If we can kind of include the epistemic uncertainty as part of the computational graph of the neural network, then at inference time, it's just going to be one forward path computation to compute this epistemic uncertainty, which is a huge advantage in practice. So now let's think about what epistemic uncertainty is supposed to capture. Unlike aleatoric uncertainty, epistemic uncertainty is sort of second order or meta uncertainty. Okay, meaning that normally your neural network is supposed to capture aleatoric uncertainty as using some kind of distribution, right, over the outputs. But now what you're caring about is the distribution of these distributions. So your network is producing some distributions, but what I want is some posterior, right? And each of the samples in the posterior is responsible for one distribution, yeah, one kind of aleatoric distribution in your output. So in a sense, what your posterior is encoding is some kind of distribution over distributions. And using this kind of way of thinking, maybe the distribution doesn't really necessarily have to be kind of stemming from the distribution over the parameters. Because eventually, like, what do you do with those parameters, right? You just take the average of the output distributions, right? So maybe the starting point doesn't really have to be from the parameters, but like conceptually, if you can just take some prior distributions of these predicted distributions of each of the model, right? Then we can basically treat these as some kind of replacement for posterior. So I'll show you a few more kind of visualizations to kind of make this even clearer. So normally you have just the prediction of mu and sigma as part of the computational graph and then do negative log likelihoods, but you kind of insert one kind of intermediate layer before predicting mu and sigma directly. You're predicting alpha, gamma, alpha, beta, gamma, and nu variables. And they are basically defining the meta distributions for mu and sigma squared. So if you're familiar with Bayesian statistics, these are essentially kind of conjugate prior distributions for the likelihood, which is defined by the Gaussian. So again, the Gaussian here is defined by mu and sigma. Yeah, likelihood is based on the Gaussian family. And you know, you want something that encodes the distribution over the parameters of this Gaussian, mu and sigma. And yeah, ideally, if we know the true distribution of all these priors, yeah, then we're probably going to use them. But since we don't know them, right, then we can choose whatever we want to do there, right? And, and then the most sensible choice actually for these meta distribution is actually the conjugate priors, because then if you take like take the analytic kind of PDF for the entire for the distribution over for the negative likelihood for using alpha, beta, gamma, and nu, then you have an analytic solution if you use conjugate prior. And that's the only reason why you want to use conjugate prior here. And then, yeah, then you can define mu as the Gaussian with the mean given by gamma and the variance given by sigma squared divided by nu. And then sigma squared is now defined by the inverse gamma function defined with alpha and beta parameters. You don't need to know all these parametric families. They're just conjugate priors of the Gaussian parameters. And if you plug this in, then your negative log likelihood is again minus log of the PDF of the Gaussian. And if you plug in the PDF for this Gaussian and inverse gamma, then it turns out to be a student T distribution PDF. With it has 3 parameters inside, and each of the parameters is defined by gamma, beta 1 plus nu divided by nu, and alpha multiplied, and 2 alpha. Okay, and now your DNN is basically parameterizing the prediction of alpha, beta, gamma, and nu, and not the mu and sigma directly. Okay, so what's the benefit of doing this? Or before that, what's the intuition here? So we have an intermediate layer of predicting alpha, beta, gamma, and nu before predicting mu and sigma, before predicting the final prediction, right? So on the middle side, right, you see now mu and sigma are not a single point that is predicted by the neural network. It's actually a distribution. And the distribution over mu and sigma is defined by the alpha, beta, gamma, and nu. Okay, so given a single values for gamma, alpha, yeah, all these, right, you're going to have a distribution over mu and sigma space. And each of the points within this distribution will correspond to the distribution over the prediction. Okay, so now this distribution is kind of the meta distribution of the prediction distribution. And the interesting thing is, as you have more and more training data, you're expected to see a smaller and smaller dispersion in this meta distribution. So as you observe more and more data, your kind of commitment to a specific parameter, mu and sigma, will be kind of more clearer. And that's why you're defining aleatoric uncertainty and epistemic uncertainty in these ways. So aleatoric uncertainty is defined by the expectation of the sigma square, which is the usual choice that we have been always making, right? Also in, in heteroscedastic regression, we use sigma square as the aleatoric uncertainty, right? Because that's kind of the variation in prediction that you are expecting to see, right? But in this case, sigma square is not a single value; it's a distribution. So you take the average of these in this space, right? And now, what's fun is the epistemic part of it. Epistemic uncertainty is the dispersion of this meta distribution, and there are, I would say, different choices of epistemic uncertainty here. You can also measure the width of it or height of the distribution. In this case, you're just measuring the width of the distribution given by the variance of mu and marginalizing the sigma square, which also kind of makes sense. And this is given by this formulation here. And in this particular paper, they don't really talk about predictive uncertainty. They just assume that predictive uncertainty is given by the epistemic uncertainty. So Yeah, so this is how you come up with a single kind of computational graph, which is supposed to contain all the ingredients for epistemic uncertainty and aleatoric uncertainty. It's very neat and nice. I mean, um, but empirically speaking, you have to basically train with this kind of loss function eventually. So you're going to have 4 different heads of the neural network, and you're going to have a very complex formulation here for all the terms. And it's still good because everything is differentiable here, and you can just plug in this formulation, and the deep neural network, deep learning framework will do everything for you. And people have trained with this loss function before, so it all works. The bad thing is that it's non-convex loss function, even without the DNN part of it. And these are all related issues, but now there are also redundancies in terms of beta and nu. So beta and nu can change from minus infinity to infinity and still do not make any change in the loss function, loss value. Yeah. So once you find a solution here, actually your solution set will be at least infinite number, right? Because you can stretch nu and beta in any way you like, and you're still going to have the same loss value. That's also connected to the non-uniqueness of the solutions. It's also connected with to the non-convexity of the loss function here. And then, most importantly, it's not a proper scoring for alpha, beta, nu, and gamma, actually. There is also a paper on this, which I put here, the second paper here, very recent results, actually. So, and in practice, it also seems to struggle a bit when you try to push it to the limit. So yeah, so it also empirically works in certain cases. So that's why people are quite excited about this some time ago, and now they're seeing the limitations from theoretical side and also from empirical side. Okay, finally, let's take a look at this, and this is the last slide, from more empirical angle. And here is still the question is, now there are a lot of estimators separate for PU, EU, and AU. Are they all trying to estimate the same, the kind of quantities that they promise to estimate? Okay, and actually there was no such part in this lecture in the first iteration of this course in 2022 and 2023. It was actually one of the questions that Balint, who was a student at the time, came to me and asked me, and I said, no, I don't know. And then he decided to kind of make a project out of this. So he wrote a master's thesis on this, and he also tutored last year's course. And eventually we wrote a paper together, and that was accepted at NeurIPS as a spotlight. So that was quite an achievement. And the answer from the paper is no to this question. So empirically, all these estimators are highly correlated. So this is the kind of typical plot that you see in the paper. So you have epistemic uncertainty on the y-axis, aleatoric uncertainty on the x-axis. If they are actually encoding something different, then you should really see different variations of aleatoric and epistemic uncertainty depending on the samples. So each point is a sample in the data set. And and the data set is designed to make sure that you have cases where you have high aleatoric uncertainty and low epistemic uncertainty, and vice versa. But you don't see any of these. They are all these measures are always very highly correlated. So we need a lot more work in this domain to kind of separate these apart. So that's the current kind of the research frontier for this section.